Hey, this tutorial is about using 2D elements in SAP 2000. We were mostly talking about line element, which is like beams and bars, trusses. But if you're go really into like practice when you do some structural analysis, you will run into either a 2D analysis or a which covers mostly the plates or the like shells and all that, or a 3D elements analysis, such as solid analysis. But we're not gonna go that far. We're just gonna touch on 2D elements so that you can do your last homework. It's almost like a small project. So basically, we want to mold a cantilever beam, and then we want to find the maximum stresses. So what I'm gonna ask you to do is that you do it, first using just typical beam element, then use a kind of refined beam element, and then using the method that I'm gonna show you here, which is the 2D element or 2D analysis, and then maybe then you compare that everything together with hand calculation. So let's get started. You start it, and then you do. Actually, it kind of counterintuitive. You do a wall, which is just a plane. So then it'll ask you to enter. So basically, I would suggest you get more elements, because the more elements you get, the better your accuracy will be. Of course, that's actually true for most of the finite element methods. Then you don't want your element to be too large. So it's gonna do so this is a 24 inch by 6 inch beam, so it's 2 feet and half feet high, and then the thickness of the beam will actually be a defining area. Then you can say it's shell or plane. We just do plane, and then we add new ones, and then you can change the name if you want. And then there's plane stress and plane strain. For this case, it's plane stress. Then you don't need to worry about that. And then the thickness. So okay, maybe it's 4 inches. So it's a 4 by 6 cross section. The length of the beam is 2 feet. Okay. Oh, I should uncheck the restraint, but anyway, I just remove them. No, okay, yep, they're removed. And now, because if I wanted the cantilever beam, so I'll fix this end. So I do assign joint restraints, because it's fixed. I fixed everything. Then I wanted to add a load onto the top of it, so you just select that point and then assign joint loads force. So because this is X and Z, so we do a negative Z. Let's put maybe 10 kips on it, and we'll see what happens. So that's on it, and then now we run analysis. We don't need modal analysis. We just run the dead load, and then it'll save it. Yeah, of course, let's just save it. Okay, so now you see it actually showed you the oh, what's going on? Yeah, the computer is acting up a little bit. It showed you the deformed shape I believe I need to change to graph. Yeah, this is better. Why don't I just do this? Oh yeah, this is better. So the key is that you know how to interpret your results. So basically, you do the deformed shape. Well, doesn't work it for me. Yeah, let's switch back. Sometimes, yeah, I just don't. Maybe your version would be better and have this resolved, but apparently my version is kind of, I have to see it here. So yes, 5. Let's do 10. What's going on? Okay, but you see the deformed shape, and then if you want to know the deflection, you just just do that. Of course, you can output everything into table, but it's typically not needed that much. Then what we care about is the stress. So we'll go to here. Okay. So you need to say, okay, it's the stress of planes, because that's the element we're choosing. Dead load, that's the load case. Then there's a whole bunch of stresses to choose from. S11, that's the sigma. That's like 11. You see 11. That's a normal stress in the one direction. This is normal stress in the two direction. Normal stress in three direction. And this is a shear stress in 1-2 direction. This one is the principal stress maximum. This is the principal stress minimum. This is the von Mises stress, which is kind of you can think of it as a like absolute principal stress values, something like that. We can take a look at one by one. S11. So you can see it's 9.10 here, then go down to 0, and then negative. It's kind of linear, so actually it is true for every single cross section, but because the moment, remember, it is a triangular, so you got the most here. But this is stress distribution of this beam, and this appears to be the tensile stress, the stress in this direction. But if we do this 2-2 direction, we don't really have that much. Yeah, this contour. So basically most of the time it's like close to 0, because this is a normal stress in the vertical direction. We don't get that much, except for some stress concentration at the point you apply the load. Then you go and then you do SS3, which is typically for a plate element. It is normal stress outside of the plane of your plate, because we're using a plane stress, which means the stress outside of the plane is 0. So yeah, it's 0 everywhere. Then this is shear stress, and you can see it's actually pretty nice. Yeah, it's pretty small here, then go up, and then it is maximum at the center, then it goes down. Remember what is the shear stress distribution in your classical beam theory? So this kind of imitated that, and you can see that from this here to here, it's like the same, because the shear force are the same. And there's some distortion here, is because of the local stress concentration again. And now let's take a look at the maximum principal stress, which is tension. So it's tension here. And those are like 0 because they're mostly in compression. The maximum compression principal stress is mostly here. And then you have some concentration here because you're compressing it. Then von Mises. So this is typically very useful when you're trying to judge where is the weakest point it's gonna like fail or it's gonna yield. So just take a look. I mean, the maximum is like here, so it's your most probably place for failure is probably here and here, which it's true. It's the same that we would be expecting. So for your homework, actually, I think I would mostly just like you to compare the normal stress here around those locations with your other calculations, and then also the shear stress. Shear stress, don't go there because there's a whole bunch of stress concentrations. Just go to ending place here. Just do me a maximum here or something, and then I will want you to compare the deflection at the tip. That's it for this one. Okay, I will post the detailed requirement for this mini project on D2L as well. So thank you for watching, and see you next time.